Now the second session of day 2 of the ATAL FDP on the topic novel materials and their applications is being addressed by Dr. Ashish Kumar Panda. Dr. Ashish Kumar Panda is working as Senior Principal Scientist in Non-Destructive Evaluation and Magnetic Materials, Group of Advanced Materials and Processes Division of National Metallurgical Laboratory, Jamshedpur. Dr. Panda obtained his PhD degree in Material Sciences from IIT Kharagpur in the year 2002. His research interest is in the development of magnetic alloys and magnetic sensors. He is also experienced in non-destructive evaluation of steels and components through electromagnetic techniques. Dr. Panda has vast research experience in Slovak Academy of Science and National Institute of Material Science, Japan, under INSA Visiting Program and CSIR Raman Research Fellowship. He has about more than 90 publications in SCA journals and filed 15 patents, transferred 2 technologies, and delivered 1 device. Dr. A.K. Panda has supervised 15 MTech and 2 PhD students. Now I welcome Dr. Ashish Kumar Panda to interact with our participants.
Yeah, thank you very much. Am I audible?
Yes, sir.
Yes, sir.
Yeah, thank you. So at the very outset, I thank the organizers for inviting me, and it is definitely a wonderful program for all the faculties. And I start off with sharing my slides actually. Just a minute. Is it visible?
Yes,
Yes.
sir.
Yeah, that's nice, because more often these are the critical problems nowadays when you go online. This wasn't there when we used to appear directly. So anyway, I think in recent years we are hearing a lot of energy materials, and especially the magnetic caloric materials are gaining ground. Well, I will say that it is the need of the hour, because we know that now there is a lot of hesitancy going for the CFCs, and definitely we look for the alternative methods, alternative techniques, alternative refrigeration techniques, and of course the top of it is the materials that we re-engineer, tailor actually. So nevertheless, just to begin with, we all are aware that we are in the middle of different type of caloric materials. And now you know that the caloric materials for energy conversion technologies are gaining ground. And those who have been working on different areas, especially, I would say that there are many interesting materials. It is not only magnetocaloric, because magnetocaloric is the area pertaining to magnetic energy and consequent device development. But you know that there are the elastocaloric, which involves the materials like nickel titanium, the nitinol. So you are aware that it was once a dream project of US, and involving naval ordinances, and of course these are have been used for different applications. Especially, I have seen some of the, even in India, they have used for developing pipe crawlers. Even nitinol shows a lot of strain. So with the thermal energy, you can generate a lot of strain, and consequently you can use it for a pipe crawlers and strain devices, strain sensors even. Now secondly, there is another area where the people have been working since years. That is the rare earth based perovskites. Of course, nowadays we are not very happy with using rare earth, because looking at the lot of rare earth being imported from China and being a dominant role. So we try to look for alternatives, but nevertheless, due to their very interesting properties, here these are under the barocaloric. So when you find a thermal effect being affected by rather the compression expansion. So I find a lot of seminars and conferences where people and students even they work on perovskites because this has been a very interesting subject and very interesting properties. Now, before going to the metacaloric, I should say that there is another interesting. There was electrocaloric. I think I heard Dr. Satnam Singh talking about it, and it is of course definitely a subject of interest. And when we say electrocaloric, typically we think of the lead zirconium titanate and PZT. So what happens is the thermal control is through polarization, depolarization, and to the extent you can generate about 480 Kelvin per centimeter even at the ambient temperatures, room temperatures, and so 220 degrees it should be Kelvin. Rather, I will say these PZTs have been application not only for electrocaloric, PZTs have been applied for generating lot of mechanical stresses, even for evaluation of defects in pipes. So as to say, because they are very good mechanical wave generators. Okay, so this is what the electrocaloric materials. Now, when we talk of the metacaloric, they are basically, we have been hearing a lot about the materials like nickel based, nickel manganese gallium based, and a lot of modifications. And again, just as I said about the perovskites, here also lanthanum has been a dominating role, wherein the lanthanum based materials have been used, even the gadolinium, and so on. But we'll later on see how the nickel based and possibly these are the one of the most interesting materials, the nickel manganese based materials, which deliver not only the caloric properties, but they exhibit a lot of different properties even in the form of a magnetostrain. So this is one of it. And when we talk of all these materials, we cannot do away with multicaloric, because you know that multicaloric is a more of a say hybrid. Hybrid in the sense when we talk of the multiferroids, it uses both the magnetic properties and the polarization, depolarization properties and the electrical properties, so that the magnetic and the electrical properties can be used to deliver very, very interesting properties. And therefore, even the multi ferroics have gained ground, and people have been working a lot on the multiferroids for different applications, not only as a caloric material. Now, when we are talking of the metacaloric, so fundamentally, I just start off having a brush up with our what we have studied earlier in our undergraduates or even university levels. Basically, we know that the refrigerational principle stands on working on the second law of thermodynamics, and two important statements are very, very important. And one is the Clausius and one is the Kelvin statements. Nevertheless, we all are aware that the Clausius statement says that you cannot have a heat flowing from cold to hot regions, and we need to have a work input. That is the primary requirement has been placed according to the Clausius statement. And secondly, when we talk of the Kelvin statement, it puts a lot of stress on the heat sink. So that is what to say that it stimulates the sum and push of energy absorbed as heat from source, and that you deliver to a low temperature sink. Now gradually we'll see how these statements have been useful for not only the general principle of a refrigeration, which is either the gas based or it can be even the magnetic based magnetic refrigeration based devices. So if it is a magnetic based devices, then we what the work done is delivered through the change in magnetation of the material. That is the one of the requirement, and that is a consequence of this both these statements. Okay. Now uh, we all are aware of the energy conversion principle, and I would like to come to closer to magnetic caloric and the magnetic influence on the magnetic materials. But nevertheless, we have to always correlate it and draw the idea from what is actually happened when we take in any of the cycles, whether it is a magnetic caloric, whether it is a electrocaloric, with the polarization changes, the elastocaloric and the barocaloric. So there are the four different stages. Where nevertheless, we should not forget these fundamentals when we are going for any of the materials designed for any refrigeration. So in principle, when we start off with the caloric material, we go for a magnetization cycle and then the demagnetization cycle, and therefore we deliver a change in the temperature. Okay, so this is one of the requirements, that is essentially when we take the four stages, or in fact, many of cases, the five stages, with one of the intermediate stages in designing such magnetocaloric material. Now, in principle, when we talk of different materials, now what is a magnetocaloric material and what is the magnetocaloric effect? For those who are not into magnetism, let me tell you that the magnetocaloric effect normally it is termed as MCE, and this basically results from coupling of a system of magnetic moments with an external field, and then you undergo magnetization demagnetization cycle, and that consequently leads to cooling or heating of the system. Now, let us go further, go back rather. So what is the epoch? What is the beginning when we talk of the magnetocaloric material? So nevertheless, I think it is the most important to say that it was long back when the German physicist Warburg, it was basically he belonged to the University of Strasbourg, and it was he who discovered the magnetic cooling and magnetic caloric effect in pure iron, and possibly it was a beginning of it. And definitely a lot of work has been done by Langevin, who is basically a French physicist, and then he demonstrated that in many of the parametric magnetization can change, a reversible change of temperature can be observed. Okay. Now, later on, then it was much later, maybe after another 20 years or so, the two important scientists that they work, and just trying to bring out the history of development of magnetocaloric materials, because though sometimes we say that old is gold. Now the work has been done long back, even by Peter Debye and Wilhelm Gauck. Debye, as you know, he was a physicist, and he was associated even the University of Aachen. And when we talk of Gauck, Gauck was basically associated with University of Berkeley, and both were the Nobel Prize winners. 36 for 1936 in Debye and 1949 by Gauck. In fact, Gauck has done a lot of work in even the parametric salts, and they have found there is a reversible temperature change in using many of the parametric salts. And when you go for the adiabatic demagnetization, we will gradually come to see what are the magnetization, demagnetization, and adiabatic demagnetization in correlation with the in principle the gas-based systems. Now, when we see that what we have seen Warburg when it was Warburg, Langevin, Debye, and York, they had made a fantastic contribution, or rather the epoch of the material, the origin of the material, the phenomena. But nevertheless, you always believe that whenever the material is developed, it has to go to a technology. So there is an interface actually. Once are the people who work fundamentally on the materials, and there are the persons who bring it, who divert it into a technology. I think both have a very fantastic role to play, because on one hand you need to know the fundamentals of it, and secondly, converting it to a technology is a very fantastic work and very challenging. And many of the times, let me tell you that when you try to develop some devices, many of the fundamentals of the materials have to be extended, stressed to the application level. So going further with it, it was when we talk the materials, it was 1997, it was Snyder. Snyder belonged to Ames Laboratory, and basically it is under the US Department of Energy. And Ames Laboratory is a fantastic place. I happened to visit it for some time, and it is under US Department of Energy, and it is full of activities basically. And this Snyder, he discovered GMI, giant matter caloric effect in rare earth compounds. And possibly after gadolinium, this was the gadolinium silicon germanium based materials, and these were the first successful near room temperature magnetic refrigerator. These were the materials for the first successful near room temperature magnetic refrigerator. Now the legacy was continued actually, and we had subsequently, it was taken up by Professor Vitalis Picharsky, and of course he also belonged to the Ames Laboratory, and it is in the campus of Iowa State University, a very beautiful place, and that has been carried out. They have been working fantastically well on the gadolinium silicon germanium materials, with a lot of variation in the alloy chemistry and conjugate material properties. Now, as I said, that when we talk of the moving from fundamentals to intermediate stage, where we have an interface of materials with the technology, and finally we have the technology. And when we talk about the technology, where we cannot escape out mentioning the name of Cooltech Applications, France, and it was 2012. It was like Christian Mueller. He went on with making a magnetocaloric rotary devices, and I must say that he was also a person who was involved in many challenging projects of France, and possibly a high-speed train also. He was a member of the team of working on high-speed trains. And subsequently, Cooltech never looked back actually. Cooltech Applications in 2014, they reported the MRS, they call it the magnetic refrigeration system, at different conferences, and a few of the very well-known conferences and like exhibits are like Euroshop and European. And subsequently, they came down with the medical refrigeration, because you see that gradually, as of now also, when we go for some from strategic applications to medical applications, I think there is a lot of priority in developing devices, materials for medical refrigeration applications. And 2015 saw the first magnetic medical refrigerator. And subsequently, they were able to attain even the freezing temperatures in 2016. So this is what we can say, that from materials to technology. I just wanted to show here how the transition took place because in every country it is very important that we do not stick only to the fundamentals. Sooner or later we should try to get into the applications, and possibly that is the need of the hour. And when we come up the further, many researchers, I will say, we always know that there have been search for different materials, even the some of the metacaloric materials, the stress sensor, the thermal sensor, and of all the search, it is explored that for both the fundamental and applied research, this has been looked at the one of the highest ever search actually. Because not only for fundamentals, you see that it displays very interesting structural behavior, very interesting magnetic behavior, and to the extent when you extend it, you find that it behaves very interesting shape memory behavior. However, today I'm not going to speak on the shape memory. I'll just focus on the magnetoglyric effect. And basically, when we talk of the magnetic refrigeration, it has different application. When we talk the ambient temperature, and when we talk of correlating with the gas based on such systems or anything, we are nevertheless, we also talk of the Breton and the Ericsson cycles. And definitely it is very important to get rid of the conventional vapor cycles refrigeration. Now the point of efficiency it is important, and it is found that surprisingly it is almost twice larger cooling efficiency. Of course, they have the limitations, which we will come discuss and we will see later. And of course, when we talk of the getting rid of the gas-based refrigeration, naturally we are overcoming the effects of use of compressors and so on, and going for the low noise levels. So this is what the advantages of the caloric materials speaks. And basically, when we talk of the for practical applications, why what are the needs actually? What are the thermodynamic requirements? When we talk of the thermodynamic requirements, these materials should be stable. They should not decapitate. They should not change physically. That is the first and foremost requirement. And possibly the next requirements are they should deliver very high adiabatic temperature, adiabatic change in temperature, and of course the magnetic entropy. I especially stress the word magnetic entropy as a function of applied field. H is the applied field and T is the temperature. And when we talk of application point of view, we intend to have the properties at a fairly low values of magnetic field. Typically, you need to have properties less than 2 Tesla is very good, so that you can really realize that when you go for making a device, you are able to you use very small magnets to bring about the thermal change in the material. And another important is the good cooling power. What it means actually, it is basically the amount of entropy the generator is able to transport from the cold to the hot side. So that is the cooling power. That is sometimes RCP, relative cooling power, technically, or the RC, the refrigerant capacity. And these are the different terminologies associated with the good cooling power. And we will come across these terminologies later, how they influence the magnetoglyric properties. Well, when we say that, speak a lot of positive things about any material or any technology, they all have their limitations. When we call the limitations, we do not say that it is a disadvantage, rather these are the restraining factors. Restraining in the sense that uh, these are restraining the progress of the materials, but nevertheless, there comes the R&D. Well, when we talk of the microcaloric material, there is some high initial investment. Investment, if you take for the rare earth based materials, investment in terms of protection of the electronic components, because we are working in the magnetic fields. So magnetic electromagnetic shielding is important here. So that is the critical aspect when you go for the device making. And of course, there is the limited field strength of permanent magnets. Uh, Permanent magnets have their own limitations when you compare with the superconducting magnets. Even squids also. With the squids, you all know you can go to 5 Tesla, 7 Tesla, 14 Tesla. But there is a problem. You cannot think of using a superconducting magnet when you make a device. So you have to make a choice that you work on with a low magnetic fields sources, and typically small permanent magnets may be a good one. And of course, need for suitable magnetocoloric materials. There comes the catch that when we talk of such a thing, whether we really want to do away with the rare earth based. Of course, rare earth based, some of the things they have already revealed very good properties. But there comes the challenge, why not to modify the chemistry, the alloy chemistry, re-engineer the materials composition, and to find at least at par with the existing ones at a much lower magnetic field. And of course, we should not be hesitant to say that still there is a lack of awareness regarding the benefits of magnetic refrigeration technology. Possibly it is not developed in our place. Possibly the others have been developing a much faster rate, but there is a start always. Now let us get into the crux of the material, the crux of the subject. What happens actually when we apply? You know that the any ferromatic material, or they have the small areas of spontaneous magnetation and the magnetic domains and the respective moments. When we apply a magnetic field, what happens is the initially before the application of the magnetic field, all the moments are disordered. It is magnetically disordered. Now, when we apply magnetic field, what happens? There is the orientation of the moments, and therefore the entropy. Uh, just keep remembering that is the magnetic entropy which decreases because we are going to the more ordering state, and that causes sample to heat up. This is surprising actually. Why at all it happens? Now basically we have a combination of different entropies. It is not only the magnetic entropy, we have the magnetic entropy, we have the lattice entropy, we have the electronic entropy, all play a role, and later on we'll see how it compensates actually and why this temperature is rising. Now, what the temperature rises in the third stage, number 3, that is sure. What is the rise of temperature? We have to cool the process, cool it through some convectional methods. And here comes the role of some forced air or liquid in circulation so that you draw away the heat. Now, when you draw away the heat and when you try to cool down, draw the heat, so basically you gradually in the same magnetic applied magnetic stage, you have the moments magnetically. You bring it to the ambient temperature. But since the field is there, it is magnetically ordered. Now what you do in the 5th stage, you try to remove the applied field, so it moves to a disordered state and it is much cooler. Okay. So this is the basic mechanism that is happening, and vis-a-vis we can compare because many of us are have studied about the vapor cycle refrigeration system where we put a typical pressure and then the adiabatic adiabatic change in temperature. When we try to draw with the heat, and then there is a change in the temperature of the system. So we compare it with the magnetic refrigeration. First of all, in the very first stage, we have a adiabatic magnetization. When we try to orient it, there is the change in temperature. We raise the temperature of the system. When we there is of course a isomagnetic enthalpy transfer. So after that, we try to draw with the heat at the same applied field. Now the same adiabatic demagnetization is the factor when we try to remove the field and it disorients. So this is just to show you how the cycles are correlated more or less. Basically, you know that it is intrinsic to any magnetic properties, and there is a magnetic lattice, and that is due to the coupling of the magnetic lattice sublattice rather with the magnetic field, and which changes the magnetic part of the entropy. Now, two things are very important: the entropy of the magnetic solid, which is a function of temperature and field, and in fact, the magnetic field strength. And secondly, it is a combination. What we have, the entropy is a combination of magnetic lattice, magnetic entropy, lattice entropy, and the electronic entropy. And now let us see further what is happening actually. As I already told you, in step one, you have with the alignment of the magnetic moments, you have the decrease in entropy. And secondly, there is a rise in adiabatic temperature. Why? Because there is a rise in the entropy of the crystalline. The lattice entropy increases because we have to compensate somewhere. So that is how the lattice entropy increases, and therefore you have a increase in the adiabatic temperature. And that was even the second stage. When we, after that, you try to recirculate it, even the same moment, you bring it to the ambient, and then you apply a demagnetization field to remove the disorient the moments, and thereby cool the material. Well, there are now, let us try to understand this with a very interesting ST diagram, sorry. So basically nothing but the entropy and the temperature diagram. And when we talk of entropy, it is basically the entropy at a zero field, or when we do not apply any field. And the secondly, when we have a non-zero field, applied field, magnetic field. Looking at the plots, two important changes are very important. When we see that there is adiabatic magnetic field change, and when you do not allow any exchange with the environment, possibly, and it is in fact whether it is isentropic. When there is isentropic, so you have a lot of adiabatic change in temperature. That is when you move from from a non-applied field, or there is absence of any field to. So this is in terms of explaining in terms of ST diagrams. And second important is isothermal magnetic field change. I am repeating this because these two aspects are the most important, I will say, magnetocaloric parameters. When you go for isothermal magnetic entropy change, you find the change in two stages of entropy, S1, S0, and this is what is actually happening. I keep on repeating, when it is for any ferromatic material and adiabatic becomes positive, and magnetic entropy becomes negative when the field is increased. And when we try to draw away the field, you have a consequent decrease in magnetic order and increase the magnetic entropy. These are the basic principles on which the magnetocaloric property or the magnetocaloric property stands. Let us have a brush with some of the fundamentals. Possibly, we all have seen these equations in a some way part of our curricula, and nevertheless, we cannot do away when thinking about the Maxwell's equations, where the differential of the entropy with respect to field, and of course at a constant temperature and field. So there's a, and whether it is equivalent to the differential of the meditation with respect to the change in temperature. And when we talk of the isobaric, isothermal isobaric process, so we do not have any changes in the temperature and the pressure. So we more or less we depend, or rather equate it more on the change in the applied magnetic field. So it is the integral of the meditation with respect to the change in temperature. And magnetic entropy change is basically when we, these are very important when you try to calculate it. They calculate the entropy, magnetocaloric properties, and the magnetic entropy. So it is a basically proportional to a derivative of the meditation with respect to temperature at constant field, and of course it is a proportional change in magnetic field. And this is the second point is important when we talk of magnetocaloric properties obtained at a certain field. When we talk, say that so much of entropy has been obtained at then certainly we ask very first that what is the field you have been applied. If you are applying a very high field of 7 Tesla, 14 Tesla, so it may be fundamentally interesting, but nevertheless, it may not be actuated when you talk of the devices. A little bit more brush up with some of the fundamentals of the entropy and magnetization, Stalin, Bazarov, Wonsky, and I just want to move fast because these are some of the equations. I'm not going deep into it, but certainly these equations are being used. And again, you have the, as I told you, the total differential of the total entropy is this is equation 6. And when we have also bulk thermal expansion, we put it all in this equation and putting it all in the adiabatic equation. That is what we have. Now, when we talk of under adiabatic isobaric process, this is the relation of the change in temperature with respect to specific heat and the differential of the magnetization. Of course, the applied field is a very important factor here. And finally, we move to the, this is what the delta T adiabatic is obtainable. This is the basic equation that you derive, and that has been derived for a finding the delta T. But there is also a catch that we although say that the two important factors delta SM magnetic and delta T adiabatic are the two parameters to find the calorimetric efficiency of a material. But we should remember there are the issues. We will come to know about it. I skip off this one. Yes. Basically, in most cases, the rate of change of magnetization with temperature becomes 0 in case of magnetization at constant field of parametics and simple parametics. So we have a delta SM negative, and this is how we find the change in magnetization moment with respect of saturation magnetization and temperature. This is how it looks, and this is a simple derivative of it. Okay, so this is a simple derivative of it, and we more often use it to find the exact transformation temperature. So in case of most of the ferromagmatics, this change of magnetization is highest at Tc, and that is what we take the advantage of it when we design the magnetocaloric materials. And even in that temperature, that which is the delta SM, we show the peak around the field temperature. So, and in fact, the delta T adiabatic also shows a peak. And in the either side, we have the reduced values. So these all aspects we take fundamental equations, fundamental aspects we take considering our equations when we make the materials and apply it for measuring the properties. Now there is a what I told you that delta S max and delta adiabatic. These are the two important parameters to gauge your material, magnetocaloric material, but nevertheless there are the problems. Basically, uh, delta S max is basically the magnetic entropy change in magnetic entropy change is the amount of heat which can be induced by magnetic field. But there is a problem. It cannot be measured directly. That is the delta S max cannot be measured directly. And delta T adiabatic is a driving force for the caloric yield. You can measure it directly, definitely. And but there is a issues related to measuring the delta T adiabatic is not that easy because there are many issues pertaining to the sensors that you put on the materials, the volume fraction of the sensors of the that you put on the material, and since these changes are quite low at single cycles, naturally they may lead to large error. Therefore, although delta S magnetic change in entropy it cannot be measured directly, we go for it. And therefore, what we do, it can be evaluated from magnetic measurements or heat capacity measured in magnetic field. And this is most of us we follow for characterization of magnetocaloric materials. And in many of the literatures, they call it an indirect measurement of magnetocaloric effect. So in view of the fact that delta T adiabatic may be a directly measurement, but it may raise a lot of errors. People have designed different methods of direct measurements, and it is quite desirable. But because of the errors in the laboratory scale, we still work with the validation studies. So now let us again move to some of the theoretical concepts. This is the right side. What you see is the magnetic moments, the magnetization plots. Basically, the magnetization plots that you see has been carried out isothermally, and you see the temperatures that are ranging from say typically 330 to 380 Kelvin. So it has goes on decreasing. This is the moment has gone. The magnesium has gone decreasing with the increasing temperature. And left side, as you see some of the magnetic caloric parameters delta Sm. When you play around with two magnetic fields, H1, H2. This is the equation, isothermal magnetic entropy change. As I told earlier, this is the adiabatic temperature change, and that you desire to measure directly, but it is not that easy. And in addition to these two parameters, there are another two parameters. One is what is called as the working temperature span. When we talk of the working temperature span in the hot end to cold end, this is the span where you actually want to work your device to work, and that is a very important parameter. When you try to find out whether the efficiency of the material, it is not only the high entropy that is required, it is also the range of temperature that you are able to work. Now, in the bottom right, you find a plot. It is a peak type of plot that is a change of delta S with respect to temperature. We have the two temperatures T1 and T2 that more or less shows the start of the entropy change and the end of the entropy change, and that is the really the working temperature delta T. And last but not the least, there is another important parameter, that is the refrigerant capacity. Refrigerant capacity is nothing but it is the amount of heat transferred from cold end to hot sink in one ideal refrigeration cycle, and that is the product of the working temperature and the peak of the delta S. Okay, so these are the few parameters: delta S magnetic, delta T adiabatic, the working temperature, and the refrigerant capacity. These, when we talk of the magnetochromatic material, these are the four important parameters that we have to look into. Now, let us come to conventional or direct MC. There is other direct magnetocaloric, because I'm mentioning the word conventional or direct magnetocaloric effect, because many of the literatures when you refer, you find it is a, these are the words used, direct, and second one is the inverse magnetocaloric. When we talk of the regular ferromagnetics, you find that there is a, when you apply the magnetic field, there is a drop in the, there is, it is more magnetically ordered. Therefore, the delta SM decreases. Therefore, it is more negative. And therefore, to compensate it, there is an increase in lattice entropy, and consequently, there is an increase in the adiabatic temperature change. So it becomes positive. So what do you find? Sample heats up when the external magnetic field is applied adiabatically, right? And we come to the other effect, that is the inverse magnetocaloric effect. Now, inverse magnetocaloric effect is mostly found in materials like which may be antiferromatic, ferromatic, ferrimagnetic, paramagnetic, and of course few of the usual alloys. We'll come to know what will be usual alloys. I will mention about it. And basically, when we talk about the antiferromatic like manganese dibromide, tetrahydrate, or ytterbium iron oxide, ferrimatic, ytterbium garnets, rather ytterbium garnets. And when we talk about the paramagnetic, it is the praseodymium nickel alloy. And when we talk of the inverse, among the usual alloys, few of the inverse magnetocaloric behavior is obtained in alloys like nickel, manganese, tin. Okay, what happens actually in this case, you have a change in magnetic entropy becoming positive. Unlike the direct magnetocaloric effect, you have it becomes positive, and consequently there is a net effect on the crystal lattice, and you have a delta T is negative, adiabatic is negative. This is in principle the difference between the direct magnetocaloric effect and the inverse magnetocaloric effect. So when we talk of the transformation, basically magnetocaloric effect is related to magnetic transitions, phase transformations. And when we talk of magnetic phase transformations, few of the things are very, very important. Basically, when we talk of the phase transformation, there are two types of phase transformation. One is the first order magnetic phase transformations. What you really find, there is a magnetization shows an abrupt change at the transition temperature, and we sometimes call at the magnetostructural phase transition. And because of the magnetostructural phase transformation, you are able to get a giant magnetocaloric effect. So sometimes called as some of the papers they call it GMC. So this is observed, has been observed typically like gadolinium, silicon, germanium type, where you bring about when you apply a magnetic field, there is a change at the vicinity of the magnetic transition temperature and structurally different phases. Now what happens is you are applying a magnetic field, there is a magnetic transition something like your para to ferro, or some cases the ferro to para, and so on. But what happens in this case is this is reinforced with a structural phase change also. What I mean to say that along with the ferropara, anti-ferropara, or whatever it is, there is another crystallographic change. The crystallographic change within that temperature phase boundary, and when these two are happening together, what you find is a giant magnetocaloric effect. It is quite natural when they both join together, you have a greater change in the entropy, magnetic entropy. So, but of course, there is a cost to it. What is the cost? Is that it has some magnetic hysteresis. Now there comes the play of the role of the tailoring of the composition, and you do away with the magnetic hysteresis, because magnetic hysteresis is something you would not desire. Basically, when we make a magnetic devices or the magnetic refrigeration system, because every and now and then, if your cooling cycle shifts, that is not desirable. Now there is a second order magnetic phase transformation when we have a ferro-para transition, and this doesn't involve two complexes. Matter structural transformation you do not find much, we do not find rather, and what happens is that it is like a ferro-para transition at a skew temperature, and the moment goes gradually to zero, typically like a gadolinium, pure gadolinium. In fact, this has been used for many thermal calibration systems. Okay, and just to show how the magnetization would look like, if it is a first order magnetization or the second order magnetization. The top one, the left side, is the magnetization plots, and you see that the transition is very sharp. And as and how you go on increasing the applied field, then you are able to shift it to the right towards the higher temperature. But in any case, they have a very sharp transition, because this is the interface where we are able to bring about magnetostructural transformations, right? So when you are able to bring out both the events, therefore the magnetic transition is quite rapid. And this is simply the heat capacity. You see all the transition, whether the absolute entropic change, all are much faster, and with the effect of magnetic field, it shifts to the right. Second order magnetic phase transformation is more of like a continuum. Continuum in the sense that you do not have any structural transformations. So the drop in the magnetization, the bottom left, that the plot is, you see that it's not very drastic. So and so forth with the heat capacity and the absolute entropy change, right? So I just repeat once again. It is when you try to work on with these materials, you look for the change in magnetization. The temperature we should be highest, is observable to be highest at the TC. Similarly, the change in magnetic entropy, and of course the adiabatic temperature. These are all related. Now to show you one of the best materials that literature has, the earliest known materials, the modification of gadolinium with the addition of silicon germanium. Possibly GD2SIGE was the first one, and GD5 were the subsequent modifications. And you see, of course, the delta SM peak appearing here around 270 to 80. That is the span. And what you see here is the delta H changing from 1 Tesla to 5 Tesla. So this is how you change the magnetic field and keep on measuring the entropy. And entropy, as I told you, that we measure from the change in magnetization, isothermal magnetizations, and with increasing temperature variations, and you find the derivative of it. Now to correlate why the behavior is so, you see this is a plot of a typical like gadolinium silicon germanium. You see that there is an interface. This is a plot of transition temperature, and x-axis you have a concentration of silicon addition to it. Now we have an interface boundary between the two green bands, vertical bands. You have see that there is a transition temperature, and if you see the gadolinium silicon germanium, it is a paramagnetic, and then it forms the next transition temperature. It goes to ferromatic state, and one of the state is GD5SI4. Now, when we have a monoclinic, so basically the orthotropic, there is such type of transitions operating here. So basically, what I mean to say is typically the first order magnetic transitions in like gadolinium silicon germanium, when both the magnetic and the structural transformations reinforce together, you find a peak, and that peak goes on increasing with the applied of with the intensity of the applied field. You see the left plot that you see that the 5 Tesla has the highest entropy. Okay, 5 Tesla is the highest entropy, and the entropy goes on decreasing as you reduce the field. Now these are all under considerations when you make a device to go for a technology. Now, next, nevertheless, now let us compare some of the previously known materials. One is like the well-known, which is gadolinium. We have the entropy. Let me tell you that entropy is mostly like conventionally, we find that it is mentioned like joules per kg Kelvin. And if you talk in terms of volume units, it is a millijoule per Kelvin per cubic centimeter. So these are the basically two units that you find in literatures. And going back to the properties, you find that Tmax, the Tmax is the entropy that you find the maximum entropy, that lies around 290 Kelvin, and with the application of 5 Tesla. And gadolinium, that belongs to a classic magnetic caloric material. And but when you have modified it with the silicon germanium, you can raise the entropy to 18.6. 18.6 at a peak around 300 Kelvin, which is more or less in the case of gadolinium that you get. But you can make out that it has gone, the entropy rises more than 3 times. Okay, and that is where the first order phase transformation works. That is due to the matter structural transformations. And of course, the equivalent was when we talk of it, when we have the manganese iron phosphorus arsenide. Arsenic is there. Certainly, none of you would appreciate it because you do not want to have the arsenic in your material. It is poisonous, and despite of very interesting properties. So you would certainly look for alternatives, and some of the alternatives are subsequent ones. When we go for the nickel, manganese, copper, gallium, and basically it is a modification of nickel, manganese, gallium, and there are 2 effects basically. One thing is nickel, manganese, gallium is a peak. This is a polycrystalline, and you have a 68 joules per kg Kelvin, which you can raise it by making it a single crystal by having an entropy to 86, because that is much more facilitated in terms of magnetization as well as the phase transformation. But nevertheless, we have a proper incorporation. We can reduce the transformation temperature. So basically, the idea is we try to do away with some conventional materials and jump into making some nickel-based materials of different compositions, right? And this is how, when we compare the entropy plots, it would look like. So when you either having a nickel, manganese, copper, gallium, nickel, manganese, gallium, They are far above higher TC and entropy change in fuselage alloys. So you can bring about high temperature transformations here, and therefore that is desirable because you can tailor it to bring it to the near room temperature transformation. If your magnetic transitions is much low, much below the room temperature, so you will have a difficulty in making devices. So you would certainly like to make a transformation uh, around room temperature or little above it. Now, when we talk about these materials, as I already told, now looking at different requirements, gadolinium, silicon, germanium, these are bit they have limitations, bit expensive. Manganese arsenide, as I told you, it is bit toxic, so you would not like to have it. Nickel manganese gallium is the something you would like to work on it because there is scope of giant metabolic effect. And you see amongst all the materials, possibly nickel, manganese, arsenic, antimonite, these are high, but because of their limitations, we do not want to go for it. In the case of nickel manganese gallium, there is a scope of tailoring the properties, compositional tailoring, and not only compositional tailoring, you can annihilate at different temperatures and to raise the entropy. So you do not have any other limitations to it, and that's the reason there has been a lot of importance in working with nickel manganese based materials. Now I move to the some of the techniques that we follow in our laboratory. Basically, whenever we are taking any material, we will start off with the pure elements. We go for the arc melting. Go for the ingot casting, and arc melting essentially in some inert atmosphere. And typically, with this some a bullet type of ingots that we make it, it shows shining. You can see. See, but let me make it very clear that working with manganese is not very easy, and because if it is more electrolytic grade, so we have evolution of a lot of gases and a lot of porosity, so we have to work very nicely with it. Secondly, we also work in further modification in the processing. One is your belt spinning system that we have, and the right side that you see, what it has, it is a copper based very high speed rotating wheel. When you try to melt the alloy, you melt the alloy using induction melting, and then what you do is eject it out on the rotating wheel. And when you eject it out on the rotating wheel, you try to get the ribbons. And when you try to get the ribbons, it can be either single layered ribbon. I mean to say it is a ribbon of only one alloy, or it is a bilayered ribbon where we make ribbons of two alloys, right? And of course, we go for the optimal annealing as per the need, and we go for the magnetic caloric property evaluation, entropy, refrigerant capacity, and for that you use either a VSM, vibrating sample magnetometer, and microstructure of evaluation are certain techniques. You all know that we can go for optical SCMTM and then electron probe microscopy. And phase transformation, this is one of the most important equipment that is required for evaluation of changes in the thermal changes in the material. Just to show that these are the typically differential scanning calorimetry, or it is room temperature VSM, the high temperature VSM into 3 Tesla for meditation studies that we follow. And when we can vary the height field 3 Tesla from 50 Kelvin to 427. Of course, these are for characterization. These are for characterization of your materials to find the entropy. And you can fairly go for the high temperature VSM also up to 1000 degrees Celsius. So I'm not going details of it because it is possibly known to many others. Uh, when I talk of useless systems, why we are interested actually, because it has so far revealed many interesting properties, both matter caloric and matter strain, and many of you may be aware, I think, that it was Friedrich Husler. He was a basically German mining engineer and who studied such an alloy. So he found this alloy. Of course, he patented it in 1901 and he published in 1993. Said there was a lot of issues and there was a lot of legacy behind it. Basically, why he worked on nickel based, the non-ferrous, not on iron. So basically, the legacy goes, I think, it goes to his father, Konrad Husler, who was working on non-ferrous metals. And basically, I think the legacy continued from there, and that's the reason he came out with a very interesting series of materials. It is not only nickel, manganese, gallium came much later. Basically, he found that they named some of the alloys, even 2 parts of copper, 1 part of manganese, and tin. They showed very interesting properties. They showed a saturation addition of around 8,000 Gauss. That is around 8 kilogauss. Even that is more than your nickel. Of course, it is much lesser than iron, but it was a fantastic observation because none of them are magnetic, ferromatic rather. So, in spite of that, the exchange coupling and all those things, and these are basically the intermetallics and the line compounds, and they revealed a very high, very good potential magnetic properties, much better even than nickel. So later on, the Husler alloys stepped in. Basically, these are intermetallics. They are face-centered cubic. They are ferromatic, and there is, of course, a double exchange mechanism between the neighboring atoms. And basically, when we gradually we come to why nickel manganese gives such interesting properties. And manganese ions, they sit on the body centers of the cubic structure, and they of course carry most of the magnetic moment of the alloy. So the most difficult material, the element that is to be processed in this alloy, are the most interesting properties to reveal. Well, when I think Husler we found this alloy of this series of materials, he never thought that this would lead to so many applications like magnetic resistors, exchange biosistors, magnetocaloric materials, and so on. Rather, when it was discovered, it was the two series basically. It was like a full Husler system, X2M and Y, and when we have a X belonging to the most of the transition metals like your iron, cobalt, nickel, and you have the Y forming the 3A, 4A, 5A elements, and typically like your nickel, manganese, gallium, it belongs to the that's second Y, that is the 3A, 4A, 4A, 3A, sorry, and this combination is they gives the L21 structure. L21 structure is basically interpenetrating cubic lattices that we will see later. And second one is the C1b structure, that is almost a half Husler alloy systems, and both have been revealing many interesting properties. This is fundamentally I start off with two structures basically, with the martensitic phase and the austenite phase. Austenite is basically high temperature phase, and you step down into a low temperature phase. It is a mostly martensite, which is either can be tetragonal or rhombic. There are many other combinations of the tetragonality. In fact, primarily based on monoclinic systems and 5M, 7M that I'm going to discuss later. Basically, when what happens actually, when you go down from a high temperature to low temperature, there is a twin structure. And due to the twin structure, you have a generation of martensite phase. Basically, it is a starts with a nano twinning. Okay, so it starts with a nano twinning, and you land up in getting a martensite structure. Whether it is the symmetry is quite different. There's a lot of asymmetry, a lot of strain in it. So I go to the further this one. This is the full Husler system that typically looks like, and this is a high temperature B2 phase and low temperature L21. That is the low temperature martensite is still below the austenite, and that is a tritonal, and even the modulated, even the non-modulated ones. So this is how it looks like when you go down. It is a tetragonal, and this is the typically a phase diagram that wants to tell you what it looks like actually. That you have a liquidus level, and when you have a B2 prime and L2, L2 I told you that it's just typically the cubic interpenetrating cubic lattices. And what the plot shows is the change in manganese concentration in nickel manganese gallium. So this is how it changes, and much below that you have freeze it down, or at the lower temperature you find a martensite. The interesting thing about the nickel manganese gallium is that you are able to generate even the martensite structure even at room temperature. That is the very interesting phenomena as compared to any other steels. Okay, so when we talk of the nickel manganese system, why we are looking to interesting properties. Basically, we see that there are three things that are happening. What you see is a typical, this is something like a plot of nickel manganese gallium iron, and with respect to your the temperature change, you have a ferromantic martensite phase, then you have martensite and austenite, and then you have a non-magnetic austenite. Okay, so in this case, what you see that when you have a ferromantic martensite, then what have a ferromantic austenite. In the case of nickel manganese gallium, it is interesting point in ferromantic austenite, and then becomes ferromantic. And this is a narrow temperature zone, and this is a typical behavior that we find in nickel manganese gallium systems. When we work on with the alloy chemistry, E by A ratio is very electrons per atoms is very important. Let us go on with how it is calculated like a typical nickel manganese gallium, like your this composition we have like 7.64. It is typically 7.64 using this atomic weights and valence electrons. And why it is important to calculate the E by A ratio, the electrons per atom ratio, because this is how the martensitic temperature depends on the electrons per atom. Now, if you have designed something, you can bring about your martensitic temperature something like your here. So it's around, you can expect your martensitic temperature around 350. So you expect that below 350 you are going to land up in a martensite, and you can work with your materials. And this is how you can modify your alloy compositions. Now, I just want to catch up with some earlier work, the typical nickel manganese gallium that we have worked actually, and to tell you the role of manganese, how the manganese has to do with it. As I told you that when you decrease the temperature, then what will happen is you land up in the martensite. Martensite can be different. It can be 7M. All our M stands for monoclinic, and then you go for the orthorhombic, then there is a tetrahedral lastly by a non-modulated structure. Basically, when we talk the modulations, it is nothing but your structural repetitions. And then under certain compositions, you do not have the modulations. So it is a more of a non-modulated structure, and then you can find out within the same martensite, you can find even the two modulations, even a non-modulated and the modulated structure. This is typically map, indexed map, electron backscatter that you see in the top right. And when we talk of the matter, these materials, why what? You can modify the matter structural things, because you can modify the combination of martensite as well. You can make a combination of martensite and austenite, and you can make a combination of modulated and non-modulated martensite. So because of that, you can bring out a lot of modifications in the structure and consequently matter structural coupling. Okay, so that leads to a very high entropy change. This is typically your nickel manganese gallium with a lot of manganese variations, and we find that there is a lot of this is optical micrographs, sorry, and of a typical having a manganese 24 atom percent alloy. And you find that the manganese ingot, the top one shows a granular structure, and you magnify it. So you find that there is combination of the non-modulated and the modulated martensites. You can even identify using your X-ray diffraction. The X-ray reflection, when you go from the low content of manganese to a high content of manganese, you find that you have initially at a low manganese content a combination of austenite and non-modulated martensite. When we go tailor the material at the intermediate stage, it is a combination of both actually, austenite and non-modulated martensite. And you will see that even the modulated martensite comes into picture, that is the 7M modulated martensites. However, when we raise the manganese a very high quantity, to say manganese 27%, you will end up in a more of a austenitic state. So schematically, we are showing how the variation is. If you go for a manganese content, the bottom right side, we try to show the schematically to make a better understanding. So this is how it is happening. A very high manganese content, we have a austenite, and a very low manganese. We have some austenite and in combination with non-modulated martensite. And in intermediate manganese content, you have a lot of non-modulated and modulated martensites. So that is how this structurally characterized, and that will also be evident in your caloric properties. So these materials show quite a large grain size. Let me tell you that the nickel manganese gallium have quite large grains, something around typically like 400-500 microns, and of course it involves a lot of intermartensitic transformations. And you see that there is a lot of plate thickening in some places, and the plates are much finer. These are basically the martensite plates. The bottom optical images, you find the different martensite plates. Well, now I go to the differential scanning calorimetry just to show you some representations. What is happening when you go for the increasing the martensite? You see that the red one is the heating cycle and the blue one is the cooling cycle. So what happens is when you increase the manganese content, the entire peak gets shifted to the left. Here ES starts, it is basically the red one is the austenitic cycle, where it is the end of the martensite, start of the austenites, and it is austenite finish. Because it is a depleting martensite, and it is a enhancing austenite state. So this is how you get in the two cycles. And what you find that with increasing manganese content, it shifts to the left. So what it means that we have a more of austenite available in the room temperature. In the room temperature. This is what is exactly what we have seen when we have done the X-ray diffractions. And this is the magnetization plots, thermomagnetic plots rather. This is change of magnetization with respect to temperature measured during vibrating sample magnetometer. And it shows very interesting properties. You see that when you go for a manganese 22, so it has a fairly high austenitic start. That is the temperature. If you, this is the austenitic start temperature that has been put on the arrow has been put whatever we have got from the differential scanning calorimeter, just to indicate the position of the austenitic start. You see that it goes on decreasing. And then in the intermediate stage, we have the austenite and martensite. And subsequently, when you go for the very low temperature, then you have the martensite occurring at a much lower temperature in the case of manganese 27. So that is also evident from the thermomagnetic plots. And this is where we use the thermomagnetic plots in combination with differential scanning calorimetry to find out where the magnetic transition is happening, at the same time where the austenitic transformation is taking place. So this idea is very important when you try to find the entropy, try to find out the entropy of the material. These are the typical table that I'm not going to show. This is quite evident, but it is a set of alloys. This is just so you see that when we have a very high manganese content, we have a fairly low MS, martensitic start temperature, and of course the austenitic finish. Okay, and even you see that either when there is a very low or high, there is a TC is quite high compared to a intermediate stage where we have a low TC, purity temperature. This is some of the important findings. So we have a large DSC span. Actually, when we have a low manganese content, and when the manganese content is less, we have a martensitic start temperature is greater than Curie temperature. Okay, and austenitic start is less than the Curie temperature. So these are the inferences what you find comparing the DSC and your thermomagnetic transformations. In the intermediate range, we have the MS and AS very close to the Curie temperature. So by looking at these temperatures, we have to make a choice. Now these are the entropy plots for the alloy systems. Now you have like your what you find here is very interesting actually. Like Mn24 basically, the manganese 24, manganese having the 24 atomic percentage alloy, that shows quite high deltas, and that comes intermediately with 23, and this is the matter-structural effect on entropy. What you find is the endothermic heat flow and the entropy change. We are measuring the entropy change, plotting the entropy change with respect to the DC temperature. So you find that it is more or less overlapping with the peak entropy. So this is also a plot of entropy change with respect to the refrigerant capacity. Refrigerant capacity, as I told you, it is a product of entropy and the width of the operating temperatures. That is the low temperature and the high temperature. So what do we get from here? Basically, the delta SM, the magnetic entropy in RC, the relative refrigerant capacity, increases up to composition of 25%, 24%, and beyond that it goes on decreasing. So this is how we try to optimize the composition for this set of alloys, and it is around a span of 330 to 360. And what you find is Mn24 is an enhancement of magnetic entropy that shows around 7.7 joules per kg Kelvin and a refrigerant capacity of 162 joules per kg. So this is how the materials are characterized and the properties are evaluated. And when we go for the similar alloys, this is just to show you that when we go for the low to high compositions, this is how you have more of austenite. This is, let me tell you, this is for the ribbon. Previously, what you find out was for the ingot, alloy ingot, and ribbon that as I told you, it is melt spun. This spun on a rotating high speed copper wheel, and then you get the austenite. That is get you the ribbon. So this is also shows the fairly high austenite at high minus content, and to show all the properties together, you find that a typical your Mn24 shows a sorry, just a minute. Yeah. So this is when we compare for the ribbon and ingot with the manganese 24 concentration, you find that there is a lot of difference actually. You have a lot of non-modulated martensite and emergence of the austenite here. So, and this is for the ribbon and ingot. And when you have a ribbon, the transitions are much sharper actually. But the reason is you have a ribbon, you have a much smaller grain sizes. When you have a high manganese content, you know from this we have austenite. When you have a low manganese content, we have a martensite plus austenite. And ingot as usual has a broader DSC peak because we expect a lot of intermartensitic transformation. Okay, and at the same time it has a much high intensity of martensitic. While in the case of ribbon, we have a high austenitic phase. That's the reason you find a lot of it is a much sharper transition in case of a ribbon. So this is what we show you. The ribbons are much smaller grain size. You can understand from the optical micrographs the nickel manganese gallium ribbons against the ingots, and we find that when you plot the delta entropy with respect to temperature and compare the ingot and ribbon, we find that the entropy of the ribbon is like 8.5 and ingot is 7.7, but the ingot has fairly bit high relative cooling capacity, 147. The idea is to tell you that even with the ribbon, you can get good entropy, and they can be used for different applications. With using ribbons, you can accommodate a lot of materials, and therefore you can use it as a magnetocaloric material with a large volume fraction of the magnetocaloric material. Okay. Now this is just to tell you, I run fast because this is a modification of nickel manganese gallium with a copper addition. Now what you find is when we have it is typically a combination of different modulated and non-modulated martensites. When we have a low copper content less than 3%, we have a combination of modulated, non-modulated martensite, wherein we have a dominance of 7 in modulated martensite and so on. And schematically, I try to show you in the bottom right how the non-modulations and modulations are changing with the copper content. So this is how we can modify with the increasing in the copper content in the alloy, and therefore in the intermediate copper content, you can have a dominant non-modulated and you can reduce the modulated concentrations. Whereas at a very high copper, you can increase the modulated martensite content. And this is how the basic idea is that you can work with your alloy chemistry to change the martensite content. so that you, because this is related to your magnetostructural coupling, so that if you are able to modify the martensite, the variations of the martensite and the intermartensitic, when I say, I mean the changes within the martensitic group. It is like the going from the 5M to 7M, 7M, 14M, or even via through non-modulated martensites. So this is how you can change it, and therefore you can modify the structural phase of the material. These are simply the ingot and ribbons plots. So you find that when we go for lower to higher in the case of copper content, you can shift the martensitic transformation towards the right, and that is how you can tailor the material. You can tailor the martensitic transformations, and therefore you can work with your metacaloric effect, because you are able to also change the magnetic transition temperature. So what we learn from here is martensitic temperature increases with copper concentration, and secondly, ribbon, in the case of ribbon, martensite temperature first increases then decreases. So in the case of ribbon, you do not get a very consistent one, because there are 2 points happening. Once is you are quenching the material, and secondly there is a intermartensite combination. So that is much more complex. So, and again, just to show you, you can go for isothermal annealing. Why I use the word that you can modify the material? You can modify the material by alloy chemistry. You can modify the material by thermal annealing. These things are very important, because while going for the high entropy, it is not essentially that you prepare the material that will reveal the very exceedingly nice properties. Rather, the choice of the annealing property, annealing temperature and schedule, the time of annealing is very important. So this is something like your ingot and ribbons. When you anneal it at high temperatures, that is for 24 hours and so on, and then you get the copper 0, and this is the entropy. You can enhance the temperature span. You see that when you, in the case of either you go for the increase in the copper content, you can increase the working temperature to delta T from 21 to 30. Of course, you cannot raise the entropy, but you can raise the working temperature, you can raise the refrigerant capacity even. And the same is true even for the ribbon. Ribbon, it is not very interesting in terms of entropy, but definitely the refrigerant capacity. So there is a combination of these two properties. The delta T could increase 30% in case of ingot, and only say it could rate by 43%. So this is the I'm not going into details of the annealing temperature. This is how you anneal it. When you anneal it, you can modify from 30 hours to 100 hours, and from even with the annealing temperature, you can modify the modulations, the martensitic modulations, the non-modulated martensites, and so on. The right side is just a schematic of to understand what is actually happening. When you go for increasing the copper content, then you can go on increasing the non-modulated stabilize the non-modulated martensite, and non-modulated martensite you can increase with the ending up to 72 hours, and when you increase to 100 hours, you do not find it. You find only the 7M. So this is how it happens. And I can skip off this one, because just to show in the case of ribbon also, because the idea is to tell you that in the case of nickel manganese gallium, whatever the compositions you make, you can go ahead with annealing and modify the structures that you're finding, and you can modify the transformation temperature. I skip off this one, And I go to a maybe another couple of last 5-10 years. Uh, we are already aware of the first order transformation and the second order transformations. The second order transformation, we already showed that the ferroparatoicians and there is no structural transformations going together. So just to tell you that there is another area when we talk of the metallic classes. In fact, I move slightly away from the your business systems just to tell you that what could be the other interesting area when we talk of the metallurgic materials. You might have heard about the rapid solidification of the metallic classes, amorphous materials, and these are nothing but what you try to do. You try to freeze the metal by freeze the material very rapidly. What happens? You try to short range order. Now this is the typical temperature time plot, and this is the curve for the crystalline band. And what happens actually, if you try to pull down the metal, you try to intersect the crystalline path, and you always land up in the crystalline materials. Whereas if you try to avoid that pulling, if you want to make it very rapid, you try to avoid the nose of the crystalline phase, then you have to pull it very fast, and it is like 10 to the power 5 to 10 to the power 6 Kelvin per second. And possibly this could lead to some amorphous materials. And the first one was like a gold silicon. I'm not going into details of amorphous. I'm trying to concentrate on the material like bilayered ribbons, which you can use for a metallurgic property evaluations. Very interestingly, what you do is in a crucible that contains two compartments. We take two alloys, alloy 1 and alloy 2, and eject it out, melt it using induction melting and eject it out on a copper wheel, and you get a bilayer ribbon with the top layer like iron silicon boron and the bottom layer like cobalt silicon boron. So it almost looks like a single ribbon, right? And then we term it SLCO for a single layer ribbon and SLFE for a single layer ribbon. Single layer ribbon means it is a ribbon that is only one alloy. And bilayer ribbon is the one where you take two alloys in the two compartments and you process it out, where the top layer is one alloy and bottom layer is another alloy. Okay, so basically then I move to next slide. I mean to say that what is happening to me. This is a plot of moment against temperature for the two single layer iron, single layer cobalt, and the bilayered iron cobalt alloy. That is the bilayered ribbon. So you find a change in moment like this, and you find that the red ones is your DS, differential scanning calorimetry, and the blue ones is the multistatic transformation temperature. The very first blue line that you see, the drop, is the Curie temperature, and after that it rises up due to the rise in moment and subsequently falls down. So your DAC plot, the DAC, the red line, you see the red line peak is somewhere in the rising second stage. So what happens, the amorphous material, these are non-crystalline. So when they try to crystalline, that is being evidenced by the DAC plots. Okay, they crystallize in the form terms of iron silicon, cobalt silicide, and so on. Right, and this is the initial Curie temperature of the material of the cobalt. Cobalt shows much lower Curie temperature, and this is the higher Curie temperature in case of iron, which is evident from the bilayer. So these are the two temperatures which are important to look into. These are the low temperature transformations, magnetic transition temperatures. Of course, it is much lower than the basic transmission temperatures. So I move to the next one. These ribbons look like this. The X-ray diffraction, there's amorphous, and when you crystallize it, they form iron silicides and so on. These are the TM micrographs. You see when you anneal it, it gives the salt paper structure like the nanoparticles. in disperse the amorphous matrix. And when we try to find out the moment versus magnetic field, the first left side is the single layered iron ribbon. The top two are the single layered iron and single layered copper. You find that there is a change in inversion in the magnetization plots. The inversion is due to the change in the crystallization. As you raise the temperature, there is a crystallization, and therefore, with a change in moment, therefore you find a change in the crystallization. So what you find in the case of iron, it first decreases and then increases, and in the case of cobalt, it goes on decreasing. So it is basically the type of second phase that is generated that is modifying your moments, right? So I move further. I think this may be interesting to you because this is a plot of your entropy with respect to your temperature, and you find the single layer iron and bilayered iron phase. That is SLFE and BLFE is the temperature of transformation of the iron based alloy, and BLCO and SLCO is for the temperature transformation for the cobalt based alloy. So iron based alloy, that is higher. So in the same ribbon, you can find out two transformation temperatures and you characterize for the two different entropies. So this is the advantage of this one. And this is the moment versus temperature where you, and the arrows indicate the Curie temperature of the alloys. And it is for the single layer cobalt that goes on decreasing, as I told you earlier. This is how the moment versus temperature is obtained. Now this is a simple display of the entropy, magnetic entropy. You see that single layer entropy is 1.7. Of course, these are not very interesting in terms of your nickel manganese gallium alloy, but certainly you need much lower field. These have been measured at around 1.2 Tesla compared to a 3 Tesla. So there is a advantage that you can go for. So I move fast. I think I will move fast to the comparison. This is the one bilayered ribbon. Bilayered ribbon, you can go to delta. Okay, and this is how you can get a relative cooling capacity about 96 joules per Kelvin. I just try to go for a couple of slides. This just to compare that our work with bilayered ribbons, you can bilayered amorphous ribbons, you can get much promising entropy compared to any of the single layered amorphous ribbons. So this is how we can get it. That bilayered ribbons, you can get entropy of say 4.56 joules per kg and a fairly good refrigerant capacity of 96 joules per kg. So this is just a comparison to tell you, nevertheless, the nickel manganese gallium show high entropy and refrigerant capacity. Even bilayer ribbons, those show 4.56, but please keep in mind that we can apply very low magnetizing fields to get the entropy, and therefore the amorphous materials may be merging in future for metal-bearing materials. And I skip off all this because you can understand that as I already told, these are the advantages of the solid state refrigeration. Just to put a flavor of where it is important is, as I already told you, in abroad, everywhere, whether it is cool tech, higher, even higher is now going for the solid state refrigerations. Even Samsung, Toshiba, all these are working for refrigerant capacity, solid state refrigerant materials. And you can simply see how the economy is going to change in the next few years, and possibly advanced equipments, the electric vehicles, and so on, and demanding more this one. These are some of the European Union projects, just to tell you, and these are again the European Union projects, and US based projects, just to give you a flavor that this how the metallic materials are gaining ground and where is the demand actually. And I think it is a time out. We all work on it, and of course it involves a lot of things to it. We should have a good working fluids, and we have the search for solutions for moving parts. Of course, design of alloys is very important. These are the some of the applications. Of course, these are small applications, but nevertheless, these are going to increase. I would certainly like to acknowledge some of my definitely Dr. Satnam Singh was one time in NML. We started off work with nickel, manganese, gallium. Of course, it was for ferromatic shape memory alloy. We got very interesting properties, and subsequently, Dr. Shushmita they carried out with metallurgical materials, and subsequently, and these are my colleagues, Dr. Rajat and Dr. Mitra, who has expired, who has retired. He is not with us, but his suggestion has been there. He still visits us and gives us very good suggestions. And thank you all.
Thank you very much, sir, and thanks to you for my introduction. Nice, sir.
You are still part of us now.
Thank you very much, sir, for an interesting talk, sir. It was really informative for the audience and for me itself. It's really nice to again hear from you, sir.
Thank you.
Now it's the time for the interaction session. So I invite audience for the questioning if they have some questions. In the meantime, the audience asks some questions. May I ask, sir, we have also worked on the some direct magnetocaloric measurement systems.
Yes.
So
yeah, tell me.
Direct magnetocaloric measurement, because you have shown few slides which are indirect magnetocaloric measurements using the BSM or other type of devices.
Yeah.
You have, I think, also working now on the direct magnetocaloric measurement system. So what type of system is that, sir?
See, basically, we try to do with some sensors, temperature sensors. Direct, we have not measured actually. Direct, we did measure, but as I told you that there are very critical aspects actually. One is, as you know very well, making a adiabatic system itself is a challenge. When we talk of adiabatic system in the presence of magnetic field. Okay,
Yeah.
so that is one of the challenges. So, but nevertheless, when I visited some places like in Ring, like in Italy, they use some Peltier cells, and possibly those are the aspects that should be looked into. But frankly speaking, I do not find a direct measurement techniques where people have been using very less error the material with a very low error, because you know that in each of the cycles you drop down a temperature by certain Kelvin. You suppose you go for a magnetization demagnetization cycle, you drop down a temperature by say 1 Kelvin, by another say not even 1 Kelvin, much less than that, and keep on running it. And in the process, you have to keep on measuring it with the. There comes the point. What I observed is the temperature sensitivity. Means when you are there is a lag. Rather, I should say there is a lag in the temperature sensitivity, because the material is has cooled down, but your temperature sensor is not sensing that fast. So these are the issues. I think we should once again work together to solve this issue. And definitely, I think if there are very smart sensors, now we should see for very smart thermal sensors other than the adiabatic package. I think it needs two things to be seen: very smart thermal sensors and very ideal thermal adiabatic package for a device. And of course, the low field is very essential. like your permanent magnets, even neodymium iron boron magnets or any such magnets should work actually.
Yeah, very right, sir. But sir, opposite to that, the indirect method, which is based upon the Maxwell's equations, those are that is not so much good enough, because there might be some errors. My material may have some new phases, or it may have a different structure which is not compatible with the so already designed Maxwell's equations. So there is also possibility of some error, but we are getting into
Yeah, yeah.
actually.
Yeah, you are right actually. Frankly speaking, I would never look into measuring your entropy change from your meditation. And all of us would be very extremely happy finding the drop in the temperature with applied magnetic field and in the meditation cycle, of course. So I think definitely it is a challenge. And of course, alloy development is one of the thing. But I think when we alloy development has been going since a very long time. I think different groups are working even in India. But I think it is a device that people should think of, especially smart sensors
Yeah.
and low fit.
Yeah, so
So
this
I do agree that when you come to this structure, especially the modulated, non-modulated, and such structures, so it is quite complex. But nevertheless, I think the 2 points are important. One is your where the transformation is actually magnetic transition, I call it, not transformation. Magnetic transition is appearing, and where is the structural transformation is appearing. So that is, I think, that is can be looked into. But as you said, I think definitely for the device purpose, I think now it is very critical that we make a direct measurements.
so you have experience. Actually, we have faculties as well as from a few PhD students itself who have joined this FDP. So
Yeah.
can you please suggest to them what could be the other materials, possible materials, which could become the future material in which the magnetocaloric type of work can be done?
See, basically, you know that recent years, it is a more of a modification in nickel manganese gallium. Okay, so nickel manganese gallium, we could find that you can modify the structure with incorporation of copper, as in we found. Gadolinium, silicon, germanium, to as a beginner, it would be quite good. We never looked in details of it, but it has been definitely old workhorse, which should work to validate your system. When you are working with a very known material like gadolinium, silicon, germanium, you know that yes, this is the entropy that is reported. This is the entropy that I am getting. So your methodology of calculating the entropy is correct. Now comes your second part is your alloy development. Alloy development, I will say that to my knowledge, nickel manganese gallium has been a material where you can modify the structure a lot. I feel that, of course, I belong to the metallurgical lab, but nevertheless, not related to a metallurgy. But I think these are the simple aspects. Then, when people are working on to nickel manganese gallium, they can heat treat it, and it is a question of identifying using X-ray diffractions. And of course, now annealing is another aspect, because you know that there is a diffusion time for the manganese and nickel ions, and that diffusion time when you cast the alloy, that you more or less homogenize when you annihilate. So that is very much essential to get the full-fledged advantage of the structure. Otherwise, once the metal is not, the atoms are not nicely diffused, you might not get the advantage of the so-called the chemistry. You might have seen the chemistry something in the reports, and that is claimed of, but certainly our materials are not giving that property. It is possible that the materials, the elements have not diffused properly, and that I think the annealing is one of the aspect. Annealing for different durations, different times, so on.
Very fine. Nice. Audience, if you have any question or you want to interact with the expert, so this talk is open for discussion.
I think we have already moved to the lunch time. People may be hungry.
So I think, so in case of that there is no questions, let me thank our speaker, Dr. Ashish Kumar Panda from CSIR National Meteorological Laboratory. Sir, we thank you very much for your valuable time that is spared for us, for our audience. And it's really nice to interact with
Thank you all. Thank you very much.
Thank you, sir. Thank you very much. Yeah. Dear participants, so it's lunchtime. We will have interaction again at 2:30 p.m. So at 2:30 p.m. we was having a speaker, Dr. Shominath Roy, but due to certain problem, Dr. Shominath Roy is not able to join. So in place of Dr. Shominath Roy, Dr. K. Shanti, she will deliver a lecture. So we will meet sharply at 2:30 p.m. after the lunch. Have a nice day. Thank you all.